Hello and welcome to some further discussion about logarithms, specifically natural and common log. Today the objectives are to look at the graphs with respect to transformations of how those graphs look when you change the equation, as well as the end behavior or the domain and range, how the graph looks out at the ends. And then the second thing is something called an extraneous solution. What we're going to do is find that in some problems we get answers that when we plug them back in, they for some reason don't work. And the word extraneous implies that they're extra, they're not needed. So you remember that a very basic exponential function would look like y equals b to the x. And if we want to do some transformations, we would see some numbers showing up inside and outside that would make it stretch, shrink, shift, whatever. And the same thing will happen with logarithms. If this is our basic log function, then the transformations will have numbers that show up in places that we see here. The b is something that can change to stretch or shrink as well. Consider the following functions. Here's a basic look at what an exponential looks like. This graph should look familiar. It approaches but never reaches the horizontal axis, x. Similarly, a log function approaches but never reaches the vertical axis, because again, we're talking about inverse functions. So if you wanted to quickly take a look here, you'd see that the graph of log x, when compared to 10 to the x, is a reflection over the y equals x line. Okay, if we look at the domain and range, you're going to see a bit of a pattern here. The domain for exponentials, you can input any value for x, from negative infinity to positive infinity, but your range will always be positive in this case. There are ways to get some negative values. Of course, that involves some transformations, but for this function, just 10 to the x, you'll never get a negative output. When we look at the log function in a similar way, what was the range is now our inputs, and you can guess that what was the domain is now our outputs. So how are the functions related? You can look at it and probably make some guesses there. In words, we could say they're inverses. The domain of an exponential function is the range of a log function, and vice versa. And what that means is certain values you won't get out of an exponential, and those are the same values you can't put in to a log. So a quick comparison, and then we're going to stick with one of these two log functions. If we looked at e to the x, that base is a number slightly smaller than 3, 2.71828 and change. And now 10 as a base flies along the y-axis a little faster. It rises faster because you're multiplying by a bigger number. So if we want to just quick take a look at that, we'd see that the 10 to the x graph takes off faster. Other than that, it's essentially the same looking graph. If we look down here for log and ln, a log base 10 runs along the x-axis faster than natural log. Okay? So they look very similar, however, and we're not going to get worried about the shapes. They're the same shape essentially, a bit of a stretch there. The one thing you might want to point out is that this point, the x-intercept of 1, 0, matches up with the y-intercept of 0, 1 in both cases. So that's something when we go to graph these things, that'll be a number or a point coordinate you'll want to include as part of your graph. It helps do your transformations. Now you can notice that the y-intercept of the exponential equation corresponds to the x-intercept of its inverse function, the logarithm. And the horizontal asymptote becomes a vertical asymptote on the logarithm graph. Showed the horizontal asymptote on a previous graph. That asymptote becomes an asymptote for the output. Likewise with log, common log. So based on the belief that these are essentially, they're very similar looking graphs, we just change one of the numbers, we'll look at the natural log function to talk about our transformations. These transformations would be very similar for the common log function, and the domain and range would actually be identical. There's no changes, it's how quickly it goes up or across. So what we do with logs in terms of transformations is pretty generic. For instance, what transformations occur to the graph of y equals ln of x? And again, I could say log x, common log x, but we'll work with the natural log. Our parent function, y equals ln of x, has a graph that looks like the one shown. And you can tell by looking at the graph that all the values go from 0 exclusive all the way up to infinity. And likewise, if you follow this graph, it's very close but not quite reaching the y-axis. It goes down to negative infinity all the way up. It's hard to tell, but it keeps going up to positive infinity. So there's our range. Now, what do you think the graph of y equals negative ln of x, or what do you think the domain of this function is by looking at the graph? Take a moment, see if you can figure it out. The domain is going to be anything from 0 to infinity. Same rules apply. You're only going to input positive values. However, the output hasn't changed either, just how quickly it gets to negative infinity or positive infinity. Likewise, we put the negative inside. Now this notice this does change quite a bit. Think for a moment, what do you think the domain for this function is? Hit pause, try to do domain and range. Okay? The domain here isn't all positives. In fact, it's all negatives, because if you input negatives and then do the opposite, you're going to get your positive. And again, the 0 is exclusive. We actually can't plug in 0. That's a kind of a theoretical value. And the domain, the range goes from negative infinity to infinity. What transformations occur to the graph that I show below here? We have an x plus 2 inside the function. You should think that inside is horizontal and opposite, so instead of moving right 2, it's actually to the left 2. So in this case, we move 2 to the left, draw a vertical asymptote, which basically resembles our y-axis for the non-transformed graph. See if you can get your domain and range from this. Okay. You'll notice that now we're able to plug in values down 2, but not including negative 2. And we'll get all the way up to infinity. And for the range, nothing has changed. Okay, and so this deals with a horizontal transformation. If you look at this, you'll recognize that the plus 2 is outside of the function. That means it's going to be a vertical. It's kind of hard to tell, but the original graph obviously would go through 1, 0. So this thing's been translated up 2. And if you were to look at that then, this point 1, 2, rather than 1, 0 exists on this transformed graph. But anyway, the domain in this case is unchanged. And the range is going to be unchanged as well. Negative. And now we'll work on some slightly more complicated problems, more than one transformation in a single graph. So I've got my little notes here on inside and outside. That works for me. Inside is a horizontal change that is opposite in terms of what I might think, including the order of operations. And the outside is a vertical that is the way I would think, or is intuitive to how I would think. For instance, this plus 1 happens outside, it's vertical, and it'll make it move up as I would think. this minus 3 down here is horizontal, and I would think it's to the left on an x-axis, but it's actually going to move it opposite to the right. And likewise, my order of operations when I do my transformations would be opposite. But we'll get going on this one here. When I have two transformations in the same direction, in this case vertical, I have to keep track of my order of operations. So this minus is like a multiply, or this negative, and the plus 1 is like addition, obviously. And in the order of operations, PEMDAS, you would multiply first and then add. So I will do the reflection first and then translate. And if you don't do it in that order, you can have some problems. When I reflect over the actual x-axis. All right, so here we go. My basic graph of a natural log looks like this. Goes through the 0.10. I'm going to reflect it first, which will make it look like this. And then it gets translated up 1 unit. So then I take this thing and make sure my intercepts, so to speak, now it's not at 1, 0, it's at 1, 1. All right, what's the domain? Domain will be all values greater than 0. A couple of ways to write that. We'll use the notation we have then. And then the range, negative infinity to positive infinity. All right, second graph here. My parent function again, something like this. I want to, now I don't have two things happening in the same direction, so the order really doesn't matter. I'm going to translate up first, up 2, and then right 3. 1, 2, 3. So what I'm drawing here is essentially a transformed chorded axis that now is going to take over 1. That's going to be my new line, or my new point to hit at, what is that, 1, 2, 3, 4, 2. Now that I have that point as a target, I simply sketch my graph there. All right. What's the domain here? Well, I can see that since my vertical asymptote translated to the right 3, it's going to be 3 larger than 0. So my domain now is 3 to infinity. And then my range really doesn't get affected too much, as you maybe have started to notice. By translations, nothing really crazy happens with the range. And I'll do this one last here. Again, I put my reference graph in there. I've got 3 things going on here. I got to pay attention. I'm going to do the outside thing first, which is a translation down 3. Okay. And I really don't need to make the sketch yet. Then I'm going to do the inside, which again is my key there is opposite. So instead of doing the multiply and then the add, I'm going to do the add and then the multiply. I'm going to go reverse order of PEMDAS. It makes me go, instead of 1 to the right, I go 1 to the left. And then a horizontal reflection. So I'm going to make this graph here. It's going to be to the right 1 unit right there. That's my graph without the reflection. Now to reflect it horizontally, I'll just do a mirror over the y-axis. So that becomes a graph something like this. All right, now let's get on to the fun part of the lesson. We get to solve for x. I remember reading somewhere some student wrote Why do these math people keep losing their x and expecting me to find it? Well, it's fun, I guess. So we'll divide by 9, and we'll get log base 6 of x plus 5 equals 2. And now, hopefully you've picked up on this generic and universal kind of rule about solving logs. We rewrite as an exponential. 6 to the 2 equals x plus 5. 6 squared is 36. Subtract 5. X equals 31. And we, from the previous lesson, and in fact you can just look at this graph of the parent function here, the previous lesson showed us that we need to be able to plug in values for x that maintain a positive argument. So if we quickly look at this, 31 substituted in, we can take the log of 36, or log base 6 of 36. It's going to come up here in a moment what an extraneous solution is, so I want to get you going on this. Okay, another problem to do. Someone find my x that I lost. And this becomes e to the 3 equals x minus 4. And I'm not going to worry about what e to the 3 is. It's some irrational number. Add 4, and this will be an acceptable solution. If you have a 10 to a power, you should be able to do that, but in this case, x equals e cubed plus 4. Now we know e is positive. It's roughly 3, a little less, so that's some number like 25-ish. Add 4. You're going to definitely be bigger than 0 for your ln. And now you're ready to give one of these a try. Again, it's just going to be like the other ones, except there's a really good chance there's an extraneous solution, so make sure you check your answer. Hit pause. Okay. First, we'll apply our property about adding logs. Allows us to multiply the arguments as a single log. And then we can FOIL this out and get x squared minus 5 plus 4 is minus 1x minus 20. And we've simplified this down as far as we can go. Now we're ready to write it as a exponential. So 10 to the 1 will equal our argument, which just means it equals 10. Now, at this point, you might try to add 20. You got to remember when we do quadratics, best to have our equation set equal to 0, so we can either use the quadratic formula or factor. In this case, factoring should work. So I've got a quadratic set equal to 0. I can factor this as x minus 6, x plus 5. And then say that my solution, or solutions, is x equals 6 and negative 5. We go to check our answer, and the positive 6 doesn't have any issues. We get positive arguments, but when we plug in a negative, we get 2 negative. It wouldn't matter, either one. If it's negative, we've got some undefined issues here. So we're to a point now where we can eliminate the negative 5, our answer is x equals 6. Are there any extraneous solutions? Yes, there are. X equals negative 5 is not a solution. So, you should be ready now for the on your own and some time in class to really get into this stuff. See you in class.